Oh, it's the, did you see the button on side?
Yeah.
You got it? Okay, cool. I'll start. It started? Okay. Dearly Father, we thank you for this day. I thank you for these students. Just pray you help us to just understand all we can about Taylor's theorem and Taylor series and all that. Today, I just thank you, Lord, for these students. Pray that you just continue to help them to do their best, Lord, each day for your glory. In name I pray, Lord Jesus. Amen. Okay, so turn your homework. Excuse me. And so today, I'm going to do something in stark contrast to what I've been doing lately, which is I'm going to basically prove nothing, and I'm going to show you how to calculate things. So, as most of you are engineers, you should be happy with this lecture. I'm sorry to the math major in here. It's a sad day for us. But don't worry, there is a few definitions here that'll make you happy. So, so first of all, I'm going to turn, basically this lecture covers bits and pieces from sections 12.6 all the way to 12.9. All right, I'm basically giving you the punchline of the chapter. And we will go back and we will do pay our dues and study convergence of power series and all that stuff on a later day. I will start introducing you to some of the subtleties, but first things first, let me give you a definition. If you have f of x, all right, equal to a naught plus a1 times x minus c plus a2 times x minus c squared plus a3 times x minus c cubed plus ... In other words, if f of x is equal to the sum k equals 0 to infinity of a sub k times x minus c to the k-fold power, then f of x is a power series centered at c with coefficients a sub 0, a sub 1, a sub 2, a sub k. These are real numbers, as is c. In particular, what I'm saying is we're defining a function f that has some domain, which is a subset of the reals, to the reals. The power series is a function from the reals to the reals, all right, such that the domain is formed by all x such that this series converges, right? So we're not thinking about just one series anymore now, right? Now we're thinking about defining a function by a point. Each point gives us a different series, and so the formula for the function is being defined by a series, by an infinite sum. Let me just try to explain that. Let me try to make that more explicit to you here with a couple comments. Like, so if I plug in 0, what happens? I get a sub 0, right? Fine. 0 minus c, which is just minus c, right? And then 0 minus c squared, and then so forth. So like here's the value of the power series at minus c. The value of the power series at 1 would be a sub naught plus a sub 1 times 1 minus c plus a sub 2 times 1 minus c squared plus ... Now, I would just make a remark. Might be nonsense. In other words, it's possible that 0 and 1 are not elements of the domain of f. It's certainly possible for me to find coefficients, right? I could find coefficients a sub naught, a sub 1, a sub 2, a sub 3, so forth and so on, for which those series I just wrote diverge. Could you guys give me a formula for a sub k that would make both of those diverge? You can use one of the examples we've already covered in class. How about this? How about a sub k equals to 1? Right. I guess it depends on what c is then. Sorry. Suppose c is equal to 1, all right, for the sake of discussion. Think about c equals to 1 and a sub k equals to 1. Oh, c equals 1 is a bad choice. C equals to 2. A sub k equals to 1 would do it. That would make both of those diverge. So neither 0 nor 1 would be in the domain of that power series. All right? But what I wrote in black stands in stark contrast. If I plug in the center of the power series into the power series, what happens? 0, c minus c, 0. C minus c squared, 0 squared. So I get a naught plus 0 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 plus 0. You get the idea. So this is just equal to a naught, right? Independent, completely independent of the coefficients a1, a2, a3, a4, a5, whatever. So what I'm trying to say, well, my point here in this little calculation is this much we can say, right? C is an element of the domain of the power series centered at C. Beyond that, I don't know. We'll have to think about that more some other day. I'm trying not to think too much about domain today. I have to think about it a little bit, otherwise it's not interesting. Any questions about this? Let me give you a more explicit example. I need to erase this, if that's okay. Everybody got this? Not that I will. I'm going to erase. Sorry. So let me put an example right here. Here's the example. If you look at f of x equal to 1 over 1 minus x, what is that? Oh, that's not what I want. I'm sorry. Oh. Subtle but important distinction I need to make here. F of x is equal to 1 plus x squared plus x cubed plus dot, 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 dot. I'm defining this function to be the power series, 1 plus x squared plus x cubed, and so forth and so on forever and ever. Now you guys have studied geometric series. You can tell me with certainty that this is equal to 1 over 1 minus x if what? If the absolute value of x is less than 1, since we have geometric series, right? With a equals to 1 and the ratio equals to x, right? So that power series reproduces, right? It replicates this rational function over that particular domain of real numbers. Let me draw a picture. What's going on here? What's the center of this, by the way? C equal to what? 0. That makes this what's called a Maclaurin series, in honor of some dead Scotsman. And let's see here. He may be alive with Jesus, but he's not here with us. Let's see here. Let's see, what then? Also, what are the coefficients in this series? They're kind of boring, aren't they? For what it's worth, I think a sub k is what? Yeah, it's just 1. 1's all the way down, yeah. And yet it's an interesting series, yeah. Power series, I should say. So here's a graph. What is y equals to 1 minus 1 over x minus 1 is easier for me to think about. See, because this is a rational function. It has a vertical asymptote at x equals to 1, right? And what does it do? It's a reciprocal, right? So it like blows up like that here, and it goes down here, and it goes asymptotically to 0, like so, right? Now, that's not a graph of the function, right? That's a graph of the rational function 1 over x minus 1, which has domain all x except for 1, right? Now, if I was to graph the series, the power series, it's just a little bit here, right? It's just like this piece right here, right? From 1 not included to minus 1 not included, right? So the power series is just this particular little piece of that rational function. That's how we use power series. We use them to reproduce functions locally. I sometimes say approximate, to approximate a function locally. If I say approximate, I'm not really thinking of the full power series. What I'm thinking of is like cutting it off at some order. Another way to write this, guys, is the limit as n goes to infinity of, oh, well, I shouldn't write that here. I'm sorry. I need to stop. There's a confusion I'm going to get into if I do that. I shouldn't do that. All right, so let me try to set up this discussion about replicating a function with a power series. Let's try to have that discussion more systematically, all right? So this is the motivating discussion for Taylor's theorem, all right? I'm going to write it again over here, motivating. And so here's the deal. We're given a function g of x, which is smooth. Near x equals to c, let's say. All right? We wish for the power series f of x equals to a sub naught plus a sub 1 times x minus c plus dot, 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 dot. Or in other words, the sum k equals 0 to infinity of a sub k times x minus c to the k-fold power. I want that to reproduce g of x near x equals to c, all right? The question that I'm going to ask is this. How to choose coefficients a sub k to make this happen. You know, to make this, to be more precise, to make g of x equals to f of x for x near c. How do you make the power series? How do you make the power series match the given function? What do you do? Now, we already know something. We already know one thing, right? We discovered in our previous discussion. What happens if we plug in c into the power series? Right, so 0 told us that, you know, f of c is equal to a naught, right? And since we want f of c equals to g of c, right? That implies that I choose a naught equal to g of c. There's one out. Remember, g is given here, so I'm trying to write a sub naught, a sub 1, a sub 2, and so forth in terms of data, in terms of the function g. So that's my first, my 0th example. How about next thing I can do? Next thing I can do is I can take my power series and I can differentiate it. What's f prime of x equal to? Well, it's going to be equal to differentiating term by term. Man, I should have written more of it. Oh, well. If you look at this over here, it's easier to look at. So differentiate this term by term. What happens? A sub 0 differentiates to 0, right? And what's the derivative of a1 times x minus c? It's just a1, right? So I guess like a1 plus a2 times x minus c plus 3a3 times x minus c squared plus dot, 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 dot. I'll write the nth one, or the kth one. How about that? Yes, thank you. So if I write the kth one, it would be like k ak times x minus c to the k minus 1, right? I'm about to erase that. I'm just trying to write the same thing over here. I know it's confusing. I was mostly leaving that there to remind myself to not diverge into some other format of lecture which would have been detrimental to our combined mental health. Let's see here. So let me erase this. All right, so what happens if we plug in x equals to c into this? F prime of c is equal to what? A1, right? But that should also be equal to what? And of course, we want what? We certainly want g prime of c to equal to f prime of c, right? If two functions are equal, right, near a point, then the differential consequence of that is that all their derivatives are equal as well, right? So the functions must match at c, the first derivatives match at c, the second derivatives match at c, the third derivatives match at c, the fourth, the kth derivatives match at c. That's the data we're going to use. So therefore, a sub 1 is g prime of c. All right. 2 down, infinitely more to go. 2. Yeah, keep continuing this, exactly. F prime prime of x is what? 2a2 plus 3 times 2, a3, x minus c, plus dot, 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 plus k times k minus 1, a sub k, x minus c to the k minus 2 power, right? So from this I see that f prime prime of c is equal to 2a2, and g prime prime of c is equal to f prime prime of c. Well, what's that? Equals to 2a2 implies what? a2 is equal to g prime prime of c divided by 2. Think through it. Think through it, guys. Does that make sense? Ignoring the fact that I never proved that we could term-by-term differentiating a power series with any kind of meaning. Setting that aside, that doesn't bother you guys. Hey. The kth step, since we started from 0. The kth derivative at x is going to be what? By then, this term has moved all the way over here, right? And you've got k times k minus 1 times k minus 2, dot, 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 3 times 2 times 1, a sub k. And so, of course, we want the kth derivative of g, right? Which we write like this, guys. Parentheses sub k of c should be equal to the kth derivative of the power series at c. But the kth derivative of power series at c we just worked out is k factorial times a sub k. Therefore, a sub k is equal to the kth derivative of oh goodness gracious, of g divided by k factorial. Remember, I want to write my answer in terms of g because that's what's given. Okay, so this motivates the following definition. Given a smooth function, say g of x near x equals to c, the nth Taylor polynomial generated by g of x at c is, well, I tend to use Tn of x. I think your book uses Pn of x. Anyway, it's the sum, k equals 0 to n of, well, g k at c, derivative of the kth derivative at c, divided by k factorial times x minus c to the k-fold power. In very much related news, okay, the Taylor series for g of x, well, I should say generated by g of x, at x equals to c is the sum k equals 0 to infinity of the kth derivative at c over k factorial times x minus c. In other words, it's a limit as n goes to infinity of the nth Taylor polynomial. When I teach Calculus 1, I actually make a point of covering Taylor polynomials. And there's a good reason for that. It's the natural extension to the story we tell about linearizations. What's a linearization? Right. Let's look at here. So like t naught of x is what? It's just g of c, right? What's t1 of x? Right? You should recognize that. That's the tangent line approximation to the function at c. Right? So the first Taylor polynomial you already studied in Calculus 1. It's the linearization of the graph. What's the second Taylor polynomial? Well, that's probably less familiar. Oh, I'm sorry. Duh. That's the second Taylor polynomial. What's the third? What you're looking at is the best 0th order approximation to g, the best first order approximation to g, the best second order approximation to g, the best third order approximation to g close to the point c. These are polynomials which we can use to approximate g of x close to the point of tangency. Thinking of the first order case, right? let me show you, for example. Here's a kind of a silly, let me show you a very silly example of this. Let g of x equals to x squared. Find the Taylor Taylor polynomial of order 2. Find, well, I'm calling it T2. Find T2 of x for, let's say, c equals to 1. Let's center it at 1. All right, so follow the lead here. G of 1, g prime of x is what? 2x. G prime prime of x is what? 2. So we've got what? T2 of x is what? It's supposed to be g of 1 plus g prime of 1 times x minus 1 plus 1/2 g prime prime of 1 times x minus 1 quantity squared. But what are those values? G of 1 is 1, right? G prime of 1 is what? So plus 2. G prime prime of 1 is 2. So, oh, 2 times 1/2 is what? Right. And there you have it. Now, this is not just an approximation to x squared, right? Because x squared is polynomial, the best polynomial approximation is in fact not an approximation at all. It's in fact exactly equal to x squared. That's an algebra identity. You can check that that's equal to x squared. Right? In fact, I could have done this a different way. I could have said x squared is equal to x minus 1 plus 1 quantity squared, and I could have FOILed that out. See? I don't think adding 0 gets enough credit. Adding 0 is, yes. Or subtracting 0, yeah. Depends on your perspective, I suppose. Okay, so 12.6, you have questions like, here's a function, find the nth Taylor polynomial. Find the 4th Taylor polynomial, find the 5th Taylor polynomial, whatever, stuff like that. All you got to do is differentiate and put these together. Basically generalizations of the linearization and so forth. By the way, man, if you look at this, this is so precious. If you think about the second derivative test, this totally explains the second derivative test if you just stop and think about it, right? Because if you got a critical point, right? If you got g prime of c is equal to 0, right? Then what does this say? This says that to a good approximation, y equals to g of c plus 1/2 g prime prime of c times x minus c squared is very approximately equal to g of x. I mean, if Taylor's theorem, I haven't stated Taylor's theorem yet, but all Taylor's theorem is going to say is that for nice functions, the Taylor series reproduces the function. In other words, I can trade a function that's defined by some formula from whatever reason, through whatever means, and I can rewrite the formula in terms of how the function behaves at one point, in terms of its value, its first derivative, its second derivative, third derivative, fourth derivative, fifth derivative, and so forth and so on, all of its derivatives at one point, and in terms of this Taylor series. That's what Taylor's theorem says, is you can approximate functions by Taylor series generated by the function at a point, given nice conditions. But if you think about what that means for a critical point for just a second, it's really interesting. A critical point is a point we studied in Calculus 1 where the first derivative is 0, right? I said the function's smooth, so all the derivatives are defined, so the other kind of critical points don't come into play here. So if you look at that, think about the higher terms in the Taylor series like the cube and so forth, these are like super tiny if you're close to the point, right? Think about being close to c. Well, x minus c cubed is way smaller than x minus c squared. These are the dominant terms near the critical point. So if you look at the graph, if this is c, right? And this is, of course, g of c, what are the possibilities? Either this coefficient is what, positive or negative, setting aside the case that it's 0. If the second derivative is 0, then we have to go further, right? But what does it look like? What's the graph look like? If it's positive, it looks something like this locally, right? That's basically what the graph looks like locally. On the other hand, if the derivative is negative, then locally the graph of the function looks like a downward opening parabola close to that point, right? And so it's either a maximum or a minimum. That's the second derivative test. If you understand this, you can easily see why there must be like a fourth derivative test. If you have 3 derivatives being 0 and the fourth non-zero, if the fourth derivative is positive, it's a minimum. If the fourth derivative is negative, it's a maximum. And so the story goes. You can see all of these things from studying the Taylor polynomial. That's why I cover it in Calculus 1. Let me show you. Well, okay, there's 2 different ways we can go here. Do you guys want to see more of these kinds of pictures first, or do you want me to derive some Taylor series for functions first? Who wants to see the functions? Pictures first? Okay. Talk me into it. I did the pictures at the end of the other section. You can go either way. Sorry, I don't have my laser today. I really should get a game for this. I have this Republic of Gamers computer. I really should like put a game on it. I think it feels wrong. I was pleased with my purchase though. When I took it to Dr. Wang and I told him what computer I got, he's like, "Oh, that's a nice computer," and like I knew I'd done well, because it's hard to get Dr. Wang to speak well of a computer. I don't know if you know this or not, but okay, I cannot anyway. You guys look like you need a joke. So I was reading Yahoo News, as I sometimes do, I'm ashamed to admit. But I glanced upon a headline that amused me greatly, something Bill Maher said. And I don't watch Bill Maher because, well, he's an idiot. But I do agree with certain things he says. I shouldn't tell you what. But he said, and his comment I thought was an interesting comment. He said that he saw Donald Trump as the white Kanye West. And I thought, that makes a lot of sense. So, follow-up question to that is, do you think Kanye West will run for president? I think the answer to that is obviously yes, of course. Hasn't he already? Has he run? I don't know. I could see him doing it, though. Is he old enough? He's not old enough, is he? Uh-oh. I don't want to get involved in some kind of Twitter battle with Kanye. Let's see here. Be careful. I'm not on Twitter, though. It's safe. I'm safe. All right. So, do you guys tweet? I don't know. What world do we live in? It's stupid. Sorry. So what you're looking at here, guys, is let me try to explain this picture to you. All right. The dotted line is the sine function. All right? And what you're looking at is Taylor polynomials that are building the Maclaurin series for sine centered at 0. Okay? I mean, it's a Taylor series centered at 0 that we're looking at various partial sums of, basically. So the blue line is y equals x. Y equals x approximates sine x maybe just about like that much, right? You know this from physics. We tell you sine theta is equal to theta to about 20 degrees, right? Remember that? So there's a picture of it. What happens? Well, what's the next thing out here? Cube, right? So what I'm going to derive here, I'm sorry, I should tell you guys, this would make more sense if I told you we're shortly going to derive that sine of x is equal to x minus 1 over 6x cubed plus 1 over 5 factorial x to the 5th, and so forth, minus 1 over 7 factorial x to the 7th, plus 1 over 9 factorial x to the 9th, and so forth and so on, forever and ever. Plus minus, plus minus, plus minus, plus minus. I referenced this the other day by plugging in 1. I plugged in 1 to this, and that's where that sine of 1 came from, remember? Anyway, more on that later. So here we go. So if you look at this, this is the sine function, right? And you can see how this is working. Like the green is the cube. It's just x minus 1/6 x cubed. That's the green. Oh man, I've got a green like that in my office. I forgot to bring it. Oh well. It's too late. So that's the green function, the very lime green there. Then if you go all the way, do I have purple? I've got purple. Woohoo. This guy, these first 3 terms, is that light purple. See that light purple? It's like its dominant term is next to the 5th, which, like that, right? So see that? But if you look at the purple, the light purple, it follows, see, it only leaves the sine function about right here. See that? Goes further out. Now the cube, you can start seeing it leave the sine function around here, right? It's definitely going further than the blue line. It's kind of hard to see, but it does, all right? Then what's next? The 7th power. Where is that in this picture? What color is that? The yellow. Yeah, I got no yellow. So as you can see, it follows sine all the way past what? Like, it looks like it's only leaving sine by the time it gets to like x equals to minus pi, right? It looks like the yellow has followed sine for a full cycle to a very good approximation, right? At least as far as you can see on my graph. So if I take the 7th order approximation to sine, I can follow it 360 degrees, or 2 pi. The next term, the 9th, would be the... Oh, you're right. The 7th was the dark. I'm sorry. Thank you. Thank you. Yeah, because it should be like a negative, right? And the 9th one should be a positive. So that would be the yellow. The yellow is the 9th. That was my point. Is by the time you get to the 9th power, you can follow sine for a whole cycle to a very good approximation. Okay. We'll make that more precise. We'll explain exactly how you can get exactly close as you'd like. We'll give estimation theorems that will make that precise. I think we already have the tools we need to do that because it's alternating. Anyway, isn't that interesting? I don't know, I think it's interesting. Who would have thunk that you could graph sine using a polynomial? And the thing is, you can keep going. You can get as many cycles as you like of sine, pretty much exactly, by just taking a sufficiently large Taylor polynomial. Isn't that weird? I don't know, I think that's weird. So that's my example here. See if I have any other ones. I'll come back to this some other day, but we will even study theorems, right? So like I can approximate the green, the red function is the function that I'm trying to approximate. And I can approximate that with the second Taylor polynomial, right? This is obviously not something second order, it's higher order. I can approximate the red graph with the green one, right? And I have an approximation theorem that will say my error is at most a certain amount, a certain tolerance. I've graphed the error tolerance in the gray bar. That's from Lagrange's remainder theorem. And as you can see, the green is close to the red within the given tolerance in where it's supposed to. Like we'll be able to not only just approximate functions, but approximate as closely as you like once we meet the conditions of certain theorems. That's one of the things we're going to work out. You can use this to do things like explain, like in my notes here, I actually have an account of how close the force F equals mg is to the real force of gravity, which is gmm over r squared. And I come up with an error in the formula. I come up with a specific error for what is lost by not using this versus using the mg formula in terms of the altitude, an explicit error in the altitude-based error formula for f equals to mg is something we can derive. Now, I shouldn't do that right now. We don't have the tools yet, right? But we can come back to this. That's the kind of thing we can do here. Let me put this away. I'll try to give you a link to whatever it is we were just looking at. When I have a chance. All right, so what I want to do for the remainder of class is to actually calculate the Taylor series generated by various formulas, and I want to show you some of the things we can do with them. So first order of business is to calculate the Taylor series for the exponential. I'm going to do it up here. It won't take long. So if there are any questions about this calculation, you should ask me now before I... All right. Example. Find Maclaurin series, which is just a sneaky way of saying Taylor series centered at 0. For the exponential function. All right, what's the first derivative? What's the second derivative? Okay. You see where this is going. The kth derivative is equal to, e to the x. Okay, so basically, let us stick a fork in it. Well, let's plug in 0, right? It's 1, right? I mean, for all k, right? So put this together, e to the x is equal to, remember the Taylor series generates g of 0 plus g prime of 0 times x plus 1/2 g prime of 0 times x squared and so forth, right? Plugging in, these coefficients are all 1, right? So what we get is that e to the x is equal to 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed, and so forth and so on. Now, let me write that in terms of its sigma notation. Sum k equals 0 to infinity of 1 over k factorial x to the k. So there you go. That's the Maclaurin series for the exponential. Now, there's a theory I'm glossing over right now, right? How do I know that that actually reproduces the exponential for all x? I happen to know that's true. I've not proved that or explained how you would decide whether it might be otherwise just yet. But trust me when I tell you that that series actually does reproduce the exponential everywhere. The fussy thing, as usual, is the question of domain. All right. Any questions about this? So follow-up example over here. What about e to the x squared? What would the Taylor series, Maclaurin series be for e to the x squared? Two different ways you could go here. You could directly apply the procedure for generating the Taylor polynomial, right? You could just start differentiating willy-nilly, plugging in 0. I don't recommend it. Seems like a drag to differentiate this over and over and over again, because after the first derivative, unless you just happen to be ignorant of the chain rule, in which case you can make yourself think it's easy. But hopefully that's not you at this point. Hopefully we all know the chain rule by now. I mean, if I was to use the Taylor generation formula over there, that would be annoying. Even at the second derivative, the derivative starts to get yucky, right? So instead, we use substitution. I know that e to the u is 1 plus u plus 1/2 u squared plus plus whatever k factorial u to the k, right? And then plug in u equals to x squared. You're like, is that allowed? Yes, it is. Will I prove that? Not a chance. Not in here. No, no, no. But substitution of series is in fact, rigorously justified calculation. If you look in advanced calculus books that have sufficiently much persistence. Anyway, so that's something you could prove, but I won't prove. But it's something you can do, and I will expect you to do. So here it is. So there you go. There's the power series for e to the x squared, just like that. Now, you could do it term by term like I did, right? Or you could do it at the level of the sigma notation. At the level of the sigma notation, right? Basically, I'm using that e to the u is what? Sum k equals 0 to infinity of u to the k divided by k factorial, right? And so I'm just taking that and replacing the u with x squared. And then just laws of exponents, right? X squared to the k power is x to the 2k. And there is the full sigma notation for it. Who cares? Right? Well, here's something you might care about. I think this illustrates the power of what we're doing a little bit. Integral of e to the x squared. That's something you could not do before. That is outside your grasp. At best, you could numerically approximate it if you had given bounds. Well, now I can take this e to the x squared character, and I can replace it with an infinite polynomial, a power series, which I just calculated up here, right? There's this wonderful theorem in section 12.9. I think 12.9.5. I'm not sure. It's in the section 12.9. It says essentially this. You can switch the order of summation and integration. In other words, you can take a series and you can integrate it term by term. I was differentiating a series term by term over there. None of you even so much as like shuddered at the thought. But if you think about it, technically, when I was, I erased it. But you know, when I differentiate the series, I'm pulling a derivative inside an infinite sum. If you knew more about analysis, that would be bothersome to you, because there's something that's needed analytically to make such a step. But we're being reckless today in terms of convergence, so you'll forgive me. Or you won't notice if I hadn't said this. But either way, it's okay. Anyway, the point is, you can integrate term by term. That's what I do. I just bring the integration inside. What's the integral of x to the 2k? X to the 2k plus 1 divided by 2k plus 1, right? We all know that. That one's not hard. And bam, you integrated. There's the integral of e to the x squared. No, that is not an approximation. That is an exact reproduction of e to the x squared. In fact, this is true for all x. Now, sometimes it might only be exactly true over some limited domain, like here. Okay. Like, for example, here I could tell you the integral of dx over, dx over 1 minus x. I could say, well, that's the integral of 1 plus x squared plus dx, right? And that would be equal to x plus 1/2 x squared plus 1 over 3 x cubed plus But this would only be true for absolute value of x less than 1. Actually, when you integrate, sometimes you introduce new points of convergence at the endpoints, as we'll see. Something called Abel's theorem, or Abel's theorem, depending where you're from, makes a more precise statement of that later in the chapter. But No, it's not an approximation. That's exactly the antiderivative. Pragmatically speaking, okay, fine, you got me. To actually implement this on a computer, I probably can only do finitely many terms. But on the other hand, if I want a function which reproduces the antiderivative to whatever precision you want, you can just keep as many terms as you need, and that's exactly the polynomial which reproduces the antiderivative up to whatever order you want. This is used throughout physics and science, and any mathematically based science uses this idea of power series in a lot of places. Yep.
So maybe just the first 5 terms.
Right. In the green, what I've done is instead of doing this, what I did was I just directly, to see where the green came from, if you look up, there's 2 different ways of calculating here, right? Like the full series versus just the first few terms. So here I'm illustrating, if you don't want to get into the summation k formula, blah, 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 you can also do term by term, right? Integral of 1 is x. The integral of x squared is 1/3 x cubed. This integrates to 1/10. That integrates to 6 over 7. 6 times 7, 42. But you can easily see that these coefficients are also checked here. If you just plug in, like k equals 0 gives me 1 times 1. K equals to 1 gives me 1 times 3. K equals to 2 gives me 1 times 5. Oh, excuse me, k equals 2 gives me 2 times 5, which is 10. If I plug in k equals to 3 here, I get 6 times 6 plus 1, which is 6 times 7, which is 42. So you can check also. Any questions? All right.
Yeah, I got one, sir.
Yeah, go for it.
So, right there at the top, you got the green line, line right there.
Yep.
1 over x squared plus 1 over 2x to the 4th and so on. Besides writing all that at the bottom of it, can I just go ahead and just do the integration rather than writing all that at the bottom? And I know 1 is going to be x, and the x squared is going to be 1 over x.
Well, it depends on the question. I do want you guys to understand the summation notation, right? There's a time and a place for one and for the other. Now, if I ask you to find the full series, the full series for the antiderivative of something, or find the full series solution of blah, that kind of obligates you to use the summation notation, right? But on the other hand, if the question just says, find the first 3 terms in the approximation, then what I've underlined in green will work. That'll be enough. Depends on the question. I want you to know both. All right, so there's the exponential. And there's an example based on a substitution for the exponential. What's next? How about Cauchy and Cinch? Right? What? It looks horrible. It's not horrible, though. You guys got to take it one step at a time. Look, Cauchy is g of x. What's the derivative of Cauchy? Cinch. What's the derivative of Cinch? Cauchy. What's the derivative of Cauchy? Cinch, Cauchy, Cinch, Cauchy, Cinch, Cauchy, Cinch, Cauchy. Oh, you get the idea. So the point here is that the 0th, the 2nd, the 4th, the 6th, these are all Cauchy, right? The 1st, the 3rd, the 5th, the 7th derivatives, and so forth and so on, forever and ever, are Cinch for the function hyperbolic cosine. When you plug in 0, Cauchy of 0 is 1, Cinch of 0 is 0. All right? So the Maclaurin series for hyperbolic cosine is just this. This is the Maclaurin series. Hyperbolic cosine, right? Now, you can do the same thing for hyperbolic sine. Almost the same calculation, right? If you differentiate hyperbolic sine, you do what? You get sine, then Cauchy, then Cauchy, then Cinch, then Cauchy, then Cauchy, then Cauchy, then Cauchy. You know where I was going. So the even derivatives for Cinch are Cinch, and the odd derivatives for Cinch are Cauchy. Same story, just different even and odd, right? So if we plug in 0 into the even derivative of Cinch, we get 0, because it's sinh of 0. If we plug in 0 into an odd derivative for sinh, we just get cosh of 0, which is 1, right? So what does that give us? That gives us the Maclaurin series for sinh, which is this. Right? So it's kind of the same formula, except instead of having 2j divided by 2j parentheses factorial, we have 2j plus 1 divided by 2j plus 1 factorial. And I've written out the first three terms for both. So like cosh has 1 plus 1 half x squared plus 1 over 4 factorial x to the 4th. Cinch, on the other hand, has what? X plus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th, like that.
Can you explain again how you get from the odd and even to the common?
Yeah, it's always this. Taylor series generated by g of x at x equals to c is this. So if you put k equals to 2j, for the hyperbolic cosine you get 1. If you put k equals to 2j plus 1, you get 0. Right? So I'm using the Taylor series generated at g of x formula. And I'm assuming that Taylor's theorem also tells me that, in fact, that series does replicate the hyperbolic cosine. I have not justified said analysis yet, but yeah.
If it was g of x equals cosh x plus sinh x,
Yeah.
would it just be the human at the other?
Yeah, look at that, right? I think you got something there. This is an irrelevant comment. Let me get rid of that. All right. So focus above the ruler. See this? We have 1. We have 1/2. We have 1/4, right? The blue, x, 1 over 3 factorial x cubed, 1 over 5 factorial x to the 5th. In other words, this is exactly the cosh series plus the cinch series. Well, that's good because the exponential is cosh plus cinch, remember? Yeah, I do want you to know the Maclaurin series for the exponential, the hyperbolic sine, the hyperbolic cosine. These are things you should have memorized. I say there's things you should have memorized, but on the other hand, I really want to say these are things you should be able to derive in 15 seconds. Is probably more honestly what my real opinion is. Desire. But if I can't have derivation, I'll settle for memorization. Right? But derivation is certainly possible, right? Like deriving these from Taylor's formula. Do you guys see do you see how that works? Does that make sense? Now, there's something else we should stop and, pay attention to the pattern here. Cosh is an even function, right? Its power series consists purely of even-powered terms. That is not an accident. A Maclaurin series for an even function will only have even powers in the expansion appearing non-trivially. Cinch is an odd function. It has only odd powers appearing in its Maclaurin expansion. I haven't derived it yet. I erased it. But we were looking at sine a second ago. It had only odd powers appearing non-trivially because sine is an odd function. Let's get back to that now. And any questions about this observation? Yeah.
So when you plug in like the j to j of 0, that was c is equal to 0.
Yes, c is equal to 0 in both of these. That's a very good.
That's because Maclaurin series.
Yeah, we've set c equals to 0 in both of these. It's Maclaurin, yeah. Which is just a silly, complicated. I guess we have to remember the Scots. So, although the history says that Taylor did what he did 20 years before Maclaurin, so I don't know why we're still talking about Maclaurin. I think it's because we like to say Maclaurin. It's kind of like it's fun to say, but Maclaurin. All right, I'll shut up. Now, we could go through this same calculation for cosine and sine, but that would be boring. I'm not going to do that. Instead, to understand where sine and cosine come from, let's look at it a different way. What if we took the exponential and we plugged in ix instead of x? Suppose that made sense. I mean, apparently it makes sense.